Reflection of electromagnetic radiation from sodium chloride. The unit cell side length of sodium chloride is 5.6 angstroms, and the modulus of elasticity along 100 direction is 5 times 10 to 10 newtons per meter square. Find the wavelength at which an electromagnetic radiation is strongly reflected by the crystal. Atomic weight of sodium is 23 grams per mole and chlorine is 35.5 grams per mole. So if you look at the sodium chloride crystal along 100 direction, along the 100 direction, we have the following situation. The sodium atoms and sodium and chlorine ions are separated by a distance A over 2. And so sodium chloride forms the basis of the crystal. So the lattice constant A is in between two consecutive sodium ions. So basically we can consider this as a one-dimensional lattice with diatomic basis. So we can consider this as a one-dimensional lattice with diatomic basis. Now we know that the atomic weight of sodium is 23 grams per mole. Atomic weight of chlorine is 35.5 grams per mole. If we calculate the effective mass of sodium chloride, we have, if we consider a spring that connects sodium and chlorine, 1 over mass of sodium plus 1 over mass of chlorine, this would give us 1 over mu is equal to 1 over 23 plus 1 over 35.5, and we have 6.02 10 to 23 atoms per mole, so that's Avogadro's number. So 23 divided by Avogadro's number basically gives us the mass of one atom, and this is also the mass of one chlorine atom here. And if we multiply it by 10 to minus 3, we're converting it to mass of one atom in kilograms. So 1 over mu turns out to be 4.31 times 10 to 5 per kilogram. Okay, so if we look at the dispersion relationship for a one-dimensional lattice with diatomic basis, this is basically what we have found in the lectures. We have an acoustical branch and optical branch, and at the Brilliant zone boundary we have square root 2c over mass of chlorine for the acoustical branch, square root 2c over mass of sodium for the optical branch, and then we have a maximum at square root 2c over mu. So in reality, when we consider 3 dimensions, we have 2 transverse acoustical, 1 longitudinal acoustical, 2 transverse optical, 1 longitudinal optical branches in 3D. And remember, some of these could be degenerate. And for the given lattice, for this lattice, we have a maximum angular frequency omega max square root 2c over mu. So here C is what we call the spring constant. So C is the spring constant. Now, how do we find the spring constant? So if you go back to where the spring constant comes from, it comes from the from Hooke's law, the restoring force on a spring. Note that the spring constant is defined by Hooke's law. The restoring force is equal to minus the spring constant times the displacement from equilibrium, and it has an SI unit of newtons per meter. So now we have to find the spring constant for the sodium chloride structure along 100 direction. The spring constant C for the spring, which is basically the bond between sodium plus and chlorine minus ions, sodium plus and chlorine minus, is basically Young's modulus, or the modulus of elasticity, multiplied by the interatomic distance. So interatomic distance is A over 2, which is 5.6 angstroms divided by 2. So this gives us 2.8 angstroms interatomic distance. We're basically assuming that a stretch along 100 direction has negligible effect on vertical springs, so that these springs in the 100 direction are behaving independently of the vertical springs. Therefore, we can calculate the spring constant along this direction. 5 times 10 to 10 newtons per meter square times 2.8 times 10 to minus 10, that's angstroms. This gives us 14 newtons per meter for the spring constant. So this allows us to calculate the maximum angular frequency. So this gives omega max square root 2c over mu. That is 2 times 14 times mu. 1 over mu we have found here to be 4.31 10 to 25. 4.31 times 10 to 25 square root. And this gives us 3.47 times 10 to 13 radians per second, which is 2 pi times the maximum frequency allowed. So we can calculate F max to be 5.53 times 10 to 12 hertz. So this corresponds to a wavelength lambda c is equal to lambda f for X-rays, and we have the speed of light 3 times 10 to 8 divided by the frequency, which is 5.53 times 10 to 12 hertz. So we find that the wavelength is 54 micrometers. Maximum wavelength corresponds to maximum frequency corresponds to minimum wavelength of 54 micrometers. So if I go back to the question, it's asking me find the wavelength at which an electromagnetic radiation is strongly reflected by the crystal. So wavelengths less than 54 micrometers will be strongly reflected because the frequency will be greater than the maximum frequency. So in summary, if we look at the sodium chloride crystal with a unit cell side length of 5.6 angstroms and a given modulus of elasticity along 100 direction, 5 times 10 to 10 newtons per meter square, we can view this as a one-dimensional crystal, a one-dimensional lattice with a diatomic basis. So we can see the distance between consecutive sodium and chlorine ions is A over 2. Between two consecutive sodium ions is A. We can calculate the effective mass for the spring that connects sodium plus to chlorine minus. So basically, we're considering the bond between them to be a spring. And knowing the atomic mass of sodium and chlorine, if you divide the atomic mass by Avogadro's number, you find the mass of one atom. And if you convert it to kilograms, you get 1 over mu in 4.31 10 to 25 kilogram inverse result. And because we know the dispersion relation omega versus k for a one-dimensional lattice diatomic with a diatomic basis, this has a maximum at square root 2c over mu. We know what 1 over mu is, but we have to calculate the spring constant. It is the modulus of elasticity multiplied with interatomic distance, and that's 14 newtons per meter. In reality, for the three-dimensional crystal with diatomic basis, we have 2 transverse acoustical, 1 longitudinal acoustical, 2 transverse optical, and 1 longitudinal optical branches. So this gives us omega max is squared 2c over mu, which is 2 pi times f max. A maximum frequency of 5.53 10 to 12 hertz corresponds to a minimum wavelength of 54 micrometers. So wavelengths less than 54 micrometers will be strongly reflected.